It's a great honor to have with us today Professor Mark Levi of Pennsylvania State University. He's also the head of the Department of Mathematics there. And his work concerns many areas in differential equations, dynamics, and geometry, often related to some physical aspects. And he's also written some books for popular audience, for example, The Mathematical Mechanic, which has received some awards, such as, for example, being one of the Choice Outstanding Academic Titles of 2009. So yeah, it's a great honor to have you with us here. Thank you so much. And over to you.
Thank you very much for the invitation. It's an honor for me. I have a little bit of a connection with Cambridge because when I was a graduate student, my thesis was on a problem that Littlewood wrote a very, very long, wrote an incredibly long paper, 135 pages, I think. It was one of my regrets that I could not meet him because he died the same year that I started working on this. But I did meet Dame Mary Cartwright when I made a side trip to Cambridge, and she told me some interesting stories about Littlewood, that he was thinking in terms of, he was when looking at the solutions of a differential equation, he was always talking in terms of trajectories of artillery shells because he was working on this during World War I. And okay, and another connection, well, this is maybe to the Archimedeans, is that the common theme for almost all the topics that I suggested is that the hidden Archimedean thinking in all these problems. So, and it will become clear what I mean. So Archimedes, as you know, I'm sure better than me, his trademark was, one of his trademarks was using physics in, for example, he used mechanics to discover, to compute integrals, to compute definite integrals, even though they were not called integrals in those times. And so I will just start with, of course, he didn't know about electricity, I guess, probably. But I'll start with the first, I guess the top vote getter was Euler's polyhedral formula. And this proof, I regret to say I did not invent. I learned it from Peter Lax. And here's the proof. I'll start sharing my screen on an iPad. I hope I'll succeed. So Euler's polyhedral formula. If you have a polyhedron, which is topologically a sphere, so I don't want any donut-shaped things. So let me just draw an example, something like this. And we count the number of points, meaning vertices, so zero-dimensional objects, count the number of edges. I call that number E. In this case, how many we have? 3 on top, 3 on the bottom, and 3 in the horizontal plane, so to speak. So 9, right? And plus the number of faces. These are two-dimensional, and it always comes out to be 2. And so here is a proof that this is the case for any one. We can calculate in this particular example, it'll come out to be 2, but it's not going to be instructive, so I won't do it. So here's how you can do it. Imagine that this is a wire frame. Each edge is a copper wire welded as shown. And what I do is I put a battery and connect it to 2 of the vertices. Doesn't matter which ones. So I just draw it for aesthetic reasons at the top and bottom. And I pump current through this. And let me just, to be specific, I pick the strength of the battery so that this current is 1 amp. And now this formula turns out to be, okay, I'm not claiming to give an absolutely rigorous proof, but it can be converted into a rigorous proof for a small fee. So what I want to say is that let's take it for granted a number of unknown currents, So each edge will have some current running through it, right? And so we have as many, so the number, there is a certain number of unknowns, the currents. Resistances are given. And that number of unknowns must match the number of equations that describe, that define these unknowns. And the number of equations, I'll talk about it in a second. So I'm claiming that this formula is really just a formal statement of this claim. And when I say equations, I mean independent equations. I don't want any redundant equations, so I don't write it, but I said it. Okay, so let's count the number of unknown currents. Well, of course, that's just as the number of the edges, right? That's E. Okay, let's count how many equations define them. Okay, what equations define? First of all, I'll say it on the side. Kirchhoff's law says that the total, there is no accumulation of electrons in the edges, in the vertices, right? However many, the sum of currents at each edge is zero. In other words, as much enters as it leaves. So the sum of currents, so for each edge, for each vertex, we have an equation which says that the sum of currents entering this edge is zero, by which I mean the entering current is counted with a plus and exiting counts with a minus. So in other words, we have the number for each vertex, we have a current. However, this number is has one redundant equation because, for example, I can circle this part of the graph, so to speak, right? And however, if I know the currents at the vertices of this graph, I know that if I treat this whole graph as one unit, I know however much leaves this one, enters this one, this vertex. So this one equation is redundant. So I really should say V minus 1, sorry, I need to change color. V minus 1, this is the number of equations for the vertices. Okay, and plus we also have the condition that the sum of voltage drops around each face is zero. It's like the gravitational field, right? You go up, if you make a circuit around the hill, you go up and you go down, and the net change in your potential energy, which is essentially the height, is zero. And the same exact thing happens in electricity because voltage is nothing but just the potential energy of a unit charge. So the same way potential energy, so the sum of voltage drops is zero, and each voltage drop is given by resistance times the current. So voltage drop is defined by the current and vice versa. So in other words, for each phase, we have one equation. So, and in a similar way, one of those is redundant. Let me not go through this, okay? And that's it, we got the formula. E equals to, this is equivalent. So that's it. That's Euler's, proof of Euler's. Well, I should probably not say proof, but close. Okay, so what was the next vote getter? The Cauchy-Schwarz inequality, yes? I forgot to mention one thing. So what if the polyhedron is not topologically a sphere like it is in this drawing? What if, for example, the polyhedron is like a torus, right? So you can make a torus like this, right? So basically cut center line. So what happens then? So let me just draw it as a smooth torus, right? Where does this, what happens in this case? Well, in this case, we have two other non-contractible loops. This one and this one. And we have to also say that the sum of voltage drops around each of them is 0. So that means we get 2 extra equations, 1 per loop. So on the right-hand side, we would then have to add 2, 1 for one circuit and 1 for the other. And you see, and then we get V minus F plus E0 for the torus. Okay, and as you see, every time you add a handle, you add 2 to the right-hand side, because you have, for each handle, you have 2 more equations. So if we had, well, basically, yeah, this is really, this torus is really a sphere with a handle, right? We can deform it and imagine it's, yeah. So we just added a handle and we get 2 extra. So maybe I should draw it. So if we add whatever we had before, but we add a handle, so then we have an extra circuit like this. Sum of voltage drops must be 0, and another circuit like that. Right. Okay. So one could also formulate this in terms of plumbing instead of electricity. One can think of these as tubes carrying water, and instead of battery, you can think of a pump, and pumping 1 gallon per second through this arrangement of tubes, and the same thing will happen. Kirchhoff's law just would say that there is no leak in any of the vertices, and there is no one adds water in the vertices. And the condition on the sum of voltage drops simply says that the sum of changes of pressure is 0. When you go around, the pressure comes back to where you started.
Well, I think this is hard to generalize to like 4 dimensions, because in the formula for the Euler equation, we can have the 3-dimension cells of a polyhedra, but
Yes.
does Kirchhoff's law generalize to the 3-dimensional cells like that?
Well, I don't know. That's a very good question. How do we think of currents? It's current is kind of a one-dimensional thing. So it's a good question, to which I unfortunately don't know the answer. Yeah.
There's another question in the chat asking about a polyhedron that is topologically a sphere but containing a ring-shaped face, which
Oh, so in other words, it has a boundary.
I think that's probably what it means, yes.
Yes, it's a good question. Yeah, there must, I don't think so, because you can, well, I don't know the answer. I have never thought about it, but I think one can probably come up with the answer by erasing, by adding and erasing, or by maybe adding, starting with this thing like this and erasing. So what I mean is, if you have something like this, right? So this is a hole, and this is a surface. This everything outside this hole is a surface. So it's basically really, then it's just a disk, right? So it's a disk in the plane. You can flatten it. And what is, yeah, and then I guess you have some kind of a partition of the disk into, and one can probably figure it out. So if you erase this vertex, you also erase this guy. And so there is a cancellation, I guess. So it's probably the same as for this. Okay.
Yeah, thank you.
Should I continue with the next topic?
think so, yes. The next one seems to be the Cauchy-Schwarz inequality.
Okay, good. So this one, I was once biking up the hill and kind of suffering because it was a tough ride. So I saw a stream going in the opposite direction, obviously. And so I thought, what would it mean to say that the water just tends, like everything, tends to the state of the least potential energy? So here's what I realized, that it's a totally trivial observation, but never realized. So imagine take a collection of cylinders of various cross-sectional areas standing on the table. I'll just draw 3. And connect them by thin tubes with a valve. And fill them to different levels with water. And write down the potential energy of the water. And I call it potential energy of the old configuration. And then I open the valves and let the water settle to the same level. Of course, potential energy will become less. Let me write it like this. And the new potential energy is going to be less than the old one. I claim that this is nothing but the Cauchy-Schwarz inequality, but in disguise. So I want to convince everybody that that's indeed the Cauchy-Schwarz inequality. So this is equivalent. Let me just say it like this. So that's equivalent to saying that the sum of if you have n tuples of number, sum of squares is, I'm sorry, I'm writing it, dyslexia sets in. So I'll write it. I will not erase it. Is sum of the products squared. So that's the claim that the Cauchy-Schwarz. So this algebraic inequality is already encoded in this simple statement. So that's kind of what I mean by Archimedean thing. You know, it's kind of hard to convince me that this is not more elegant. If they're equivalent, the first statement looks so much simpler and so much more obvious intuitively, right? Of course, you can think geometrically of the Cauchy-Schwarz, and then it's saying cosine is less than 1, but still. All right, so let's see how to explain this equivalence. All right, let's give the names. Let's call the area of the base of the cylinder A, and let's call the height of the cylinder H. What's the potential energy of the water in the cylinder? It's equal to the weight times the height of the center of mass. Okay, and the weight of this, let me take density to be 1. The weight is basically area times of the base times the height, and the height of the center of mass is, of course, half the height. By the way, I could take these shapes not cylindrical, but of a different form, and then it will become Hölder's inequality. So I just chose the simplest thing, but Hölder's inequality is exactly the same thing. And so this is going to be half that. I don't care about AH squared. It's a quadratic function of the height. Okay, so the total potential energy, so the potential energy of the old one is, let me write that first. So potential energy of the old is, so before, the potential energy is the sum of these potential energies. So it's a half of A, K, H, K, k squared, where k runs from 1 to n, in this case 3. And let me actually drop those subscripts. Okay, so I'll just write it like this, sum of a h squareds, right? Is that all right? When I say sum, I mean that the subscripts are meant to be included, but are dropped for the sake of simplicity. So that's before. And then after, the potential energy is the same expression. It's a half the sum of areas times the average height squared. So it's half sum of the areas times the average height squared, which I can factor out. And we just need to find the average height. That's simple. So the volume before is equal to volume after. That's going to tell us the height. So the volume before after, okay, well, the volume before is just the sum of area times the height. And the volume after is the sum of areas times the height average, right? So therefore, the average height is simply the weighted average of the previous heights, which is not surprising. I could have just guessed it, right? So it's the sum of AKH, K divided by the sum of all the areas, right? So that's the mean value. And I can plug it in here. And you see, this guy here gets squared because of this 2. And one of them gets canceled with this. So therefore, this inequality becomes, I drop half, of course, and this becomes half AK HK squared. I'm sorry, I'm resorting to writing K, but that's the old, right? Potential energy apart from the factor 1, 2. It must be greater than the new potential energy, which is written here. So that's greater than sum of this sum squared, sum of AH squared, and divided by the single power of the sum of a's, right? Because, like I mentioned, this guy cancels with this one when it's squared and one of the sums is still remaining. And so I just simply multiply by this, so that's it. So we're done, 95% finished. So sum of AH squared times the sum of a's is at least the square of the sum of AH. And so the last thing I want to do is I call this X. Okay, let me do this. Okay. So I call this XK squared. And I call this YK squared. So I introduce variables X and Y defined like this. Notice that XK, YK squared, when I multiply them, you see, I multiply these guys together, I get A squared times H squared. So in other words, XY is AH. So this is XY. And so we're finished. So this gives us sum of X squared, Y squared. Okay, so this algebra is uninstructive and boring, but I just did it to show that indeed it's equivalent. But I think what's interesting is that it allows you to invent an inequality. For example, if I never knew Cauchy-Schwarz inequality, I could have just asked myself, well, this statement about potential energy getting less after opening the valves, that's obvious. What does it say? And if you just, so you can discover things. Probably that's how Archimedes discovered things, some things. And like I said, Hölder's inequality applies. You could ask another there are several different ways. Here's another one I cooked up, but if you, how else can you get Cauchy-Schwarz inequality? Imagine you have Hookean springs and connected to each other. Well, let me just draw 3. And if you say, you can imagine that these masses can move left or right, they're constrained, and you hold them in some position and then let go and let the friction do its work and let them settle to an equilibrium. Again, potential energy becomes less. Again, that is equivalent to the Cauchy-Schwarz. I'm not going to do it, but you can, and to show that you have to think instead of distances, one should use forces of tension in each spring, but Cauchy-Schwarz involves 2 variables, x and y. Where's the second variable? So f is 1. Where's the other? The other turns out to be Hooke's constant, or rather it's reciprocal. Anyway, so that's what I wanted to describe.
Yeah, thanks. Are there any questions about the Cauchy-Schwarz? If not, then can I ask, could you just really briefly show what type of shapes would you use for Hölder's inequality? How would you get that?
You use polynomial shapes.
Okay. Mm-hmm.
Yeah, binomial, like a power, just x to the power. I mean, this, you see this cross-section area is just a constant, but if you
oh, so if the area depends on the height. Is what
yeah, area depends on the height, some funnel-shaped thing. And this is, you know, if this height is h, then you just take it h to some power alpha. And I don't so this other is related to alpha. Nothing after this idea makes any simple intuitive sense. It's just a calculation, but the interesting, but I think this is kind of the maximal separation of mindless algebra from something intuitive, right? So you make something intuitive, it's almost like a delta function. You say it outright, and the rest is just dumb calculation. So I don't claim any insight into that. And also, I don't quite understand why this canonical form of the Cauchy-Schwarz coming out, why is it in a hidden form? You see, it comes, Cauchy-Schwarz is a little bit hidden in this. You see, this doesn't look so nice, so symmetric. A and H don't play equal roles here. I need to symmetrize this in some way.
Yeah. Are there any other questions about Cauchy-Schwarz inequality? If not, then I guess we should probably move on to the next section. Yeah. The next highest seems to be finding curvatures in areas using a bike.
Okay, well, this is a very quick and simple thing. It actually is related to a lot of things which maybe I'll mention. Did people take, I guess there are, not everybody took, for example, complex analysis.
Yeah, probably not everyone yet.
Okay, so then I will just say, okay, so how this thing started, my interest in this started when I was in a supermarket one time, very late at night, buying diapers, I guess, for my baby. And so I was, and the cashier was somewhere in the depth of the store. And so I was waiting with a cart, and I was, the floor had these rectangular, you know, tiles, square tiles. And my shopping cart, I just mindlessly, I was tracing the front wheel, one of the 2 front wheels of the shopping cart around the circumference of the tile. And I noticed that the cart ended up rotated. So the front wheel started and ended at some point, but the cart ended up rotated. So I'll draw this for just take an arbitrary curve, doesn't have to be a square, and guide. So instead of a shopping cart, which has a trapezoidal arrangement, let's talk about quote unquote bicycle, by which I mean, so the bicycle is a segment with the front end, so to speak, and the rear end. So this is, you can think of a bike, right? I'm trying to draw a saddle. And these points are the contact of the wheel with the contacts of the wheel with the ground. And there are two things. The segment must move in the plane without changing its length. And moreover, the rear wheel's velocity must be aligned with this segment. Okay, and so, for example, here's a typical trajectory. I can move the front wheel along any path I want, and the rear wheel trajectory will have to be like this, right? So the velocity, you see, is aligned with the segment. Okay, so anyway, so if I do this, so I start with the front wheel, I start with a bicycle like this, front wheel is forced to go in a closed path. So probably have to think of a bicycle like a stunt bike where the front wheel handlebars can go all the way around 360, right? And so what's going to happen, let me redraw it here. So here's the front wheel starts here, rear wheel here. So as I go, the rear wheel will describe this path. It will go forward while I travel this way, and then the bike kind of goes backwards. It backs up, right? It stops instantaneously, backs up. And the wheel has rotated through an angle, and the remarkable thing, then I realized this angle, theta, is equal to the area of the described by the front wheel divided by the length of the base squared plus, I mean, it's not an exact formula, plus something small compared to the area. So this is good when the area is small. So you can approximately measure the area of the tile by moving the cart's front wheel around the tile and then checking out how much did the cart turn. Of course, this is a good way to maneuver the cart into so that it's parallel to the, so you can enter the, the exit lane. All right, and so, of course, I was not the first to observe this thing. It was discovered already at least in the 1860s by Holger Pritz, who was a Danish cavalry officer, and he used this to measure areas of the on the map by you can kind of, there is a Pritz planimeter. A very simple device to measure areas, and it's basically a hatchet. It's also called a hatchet planimeter. You can take an axe, and its blade is sharp so that, and it has a pointer. And what you do, you guide this pointer around, let's say you want to measure the area of the lake on the map. You guide the pointer around the lake, and you let this edge slide on the paper. It will not sideslip because it's sharp. It moves like the rear wheel of the bicycle. You could, of course, use a scooter to also, and you can measure the area, the angle by which it turned. Okay, so how can you, so this bicycle dynamics is surprisingly rich. So there was a nice thing that was discovered by, let me actually say first what I promised, right? So I promised to describe how to measure the curvature using a bicycle. So here's how. You can take the curve. Let's say you want to find the curvature of this curve. Well, take the bicycle and put the rear wheel of the bicycle here, make the bicycle tangent, and you insist on the tangency as you move the rear wheel forward. You roll the rear wheel on that given curve. And you watch the front wheel go. So the front wheel is going to be like this. And here's the remarkable thing, the intersection of the, look at the straight line of the axle of the wheel. Extend the axle of the wheel as a straight line. Do the same for the front wheel. And the point where they intersect, this is the center of curvature of the rear track. In other words, it's the center of the osculating circle. So that's an interesting observation that is, I will not give the proof, but I can just outline the idea. You can pretend that there is essentially, the idea is there is no loss of generality in assuming that R is travels in a circle. You can replace this curve, the rear track, with a circle. And then the statement becomes almost absolutely obvious. And then the next observation that having replaced this by a circle didn't make a difference. And so that's kind of the idea of the proof. But I wanted to also mention an interesting thing about the bicycles. So that was discovered, to my knowledge, very recently, maybe 20 years ago. So take any curve whatsoever, without any restriction, take any curve. So given curve gamma, and it doesn't have to be a straight, a closed curve, and look at guide the front wheel of the bicycle along this curve. And the bicycle could have started in any orientation. So there is a whole circle worth of the initial directions of the bike. So you can imagine you have a whole bunch of these bicycles, so to speak, right? And all of them have the same front wheel, share the front wheel, and you guide the front wheel. All the bicycles, they will kind of peel back. You see what I mean? In this particular example, right? If the curve is long, they kind of peel back. So we basically have every bicycle starts starting direction. So let me single out a particular bike and its ending direction. So we have a mapping of the circle. So the point, let me call the point theta or x. Let me call this point actually z. That's the point z on the circle, maps onto the point w on the circle. So I can draw these circles now in the same, with the same center. So the point z got mapped to a new location w. And notice that this mapping, so we have a mapping of the circle to itself, right? The deformation of the circle. So I shouldn't call it deformation. Points slide on a circle to new locations. And that how they slide depends on that curve, but I fixed this curve, right? So the remarkable thing that Bob Foote noticed is that this mapping, the map from Z to W, has only 3 free parameters. It has to be like this. So W must be of the form and now I use complex notation. So if this is a unit circle, then Z is a complex number. So even if you didn't take complex variables, you probably know that. So there is a number theta, which depends in some very complicated way on the curve, but it's a specific number given a curve. That number is defined times Z minus A, and A is a complex number that also depends on that curve, and 1 minus A conjugate Z. So this is the so-called Möbius transformation. So that's kind of a nice thing, and this is the tip of an iceberg, and then you can find some surprising things about the bicycle kinematics. When I say bicycle, I put it in quotes because it's, of course, a simplified bicycle. But that's why I said, so I said there are three parameters. You see, there is theta, and A has real and imaginary parts. So that's three real numbers. And that's all you can get. Doesn't matter how messy or complicated this curve is, the mapping will be of such a form. And there are some remarkable consequences of this, which I don't go into. But if you want the reference, I can give you. Okay.
Yeah. Are there any questions in this? Anyone?
There is, I should mention that this formula has a very surprising explanation. If you go out of the plane, if you imagine, this is kind of sounds maybe stupid, but it gives a real clear insight into without almost no almost no calculation why this formula is true. It turns out to be this quantity turns out to be a solid angle, roughly speaking, a solid angle from which you view this area as you sit above the plane. Okay, so that it's not practical to go into the details, but that is an interesting point. Yeah.
Okay, thanks. Yeah, there didn't appear to be any questions. They're just, yeah, someone has said that this is truly remarkable. I do agree. It's very nice.
Yeah. Thank you. By the way, there is also another thing. I don't want to draw anything, but here's roughly the statement. If you are riding a bike at night, right, and you have a laser pointer mounted on your handlebars, and this laser pointer illuminates a dot in front of you, kind of maybe 10 feet ahead of you or so, right? This dot is not along the straight line of your bicycle frame. It's to the side, to the left or to the right. This distance is, roughly speaking, the curvature of your rear wheel. That's kind of an interesting thing too. In other words, you don't have to turn your head back and to see where do your axles intersect behind you, would be the center of curvature. You can see the curvature itself, well, with some factor, right? But basically, this distance is essentially, in other words, the angle by which you turn the front wheel, you could say. That measures the curvature of the rear track in some way. Okay.
Yeah. Mm-hmm. Yeah, thank you. And the next topic seems to be using flotation to find roots of polynomials.
I have a question. So, so in spheres, we have the area on the sphere that is proportional to the angle at the center. So when you say solid, the area is solid angle, do you mean that?
Yes, what I meant was in this picture here, right? Of course, this is not on the sphere, this is on the plane, but it is a small, I mean, everything I say is for small areas. So, so if you rise, let's say, take the center of mass of this region, for example, rise above it by unit distance, and then you visualize this thing with a certain solid angle. So in other words, there is, solid angle, as you say, would be a sphere, the area on the sphere, not on, Anyway, I'm sorry, I'm going off. All I want to say is that when you look at this area from above, unit distance, you see it at a solid angle, which is approximately this area. So I'm not saying this area equals, but to a small correction, it is solid angle in this area are very close. The smaller the area, the closer they are.
And does that come just from the fact that as a solid angle is the area of kind of the cup, kind of the area in the sphere, and the area you have is the area of the cross section? Is that what's happening?
Yeah, so you see, this thing is, I was hesitating to go into the details, but basically, when you see, I took the bicycle into 3 dimensions. Now, what does it mean to ride a bike in 3D? You move the front wheel, still in some closed path, doesn't matter, but the rear wheel, you see, you can also imagine the rear wheel, of course, it still moves in the direction of the rod, but there is also, you see, it's like an arrow to which you can attach fins. And the fins don't rotate, the fins also follow. So that's an additional piece of information. So there is no parallel, they kind of do a parallel transport on the sphere, you could say. In other words, these fins, when they intersect a sphere centered to the front wheel, these fins like form a little plus sign on the sphere. And as whatever the bike is doing, this plus sign, it doesn't rotate. And that's kind of a hint as to what happens when this plus sign comes back. It actually ends up being turned.
Yeah, thank you.
Yeah, if you want to know more details, I can give you a reference to a paper where this is described on 1 page or 1.5 pages. I mean, it's a long paper we wrote, but this is described on 1 page.
Yeah, thank you.
Sure. With good pictures too, by the way. So
yeah, it's always helpful.
So yeah, the floating polynomials, right? It's like Steve Stroger said it could be called watery roots or something, because roots of a polynomial. Okay, so I should qualify that this doesn't always work, but when the roots are real, then here's how we can do it. So let's take a sheet of styrofoam, flat sheet of styrofoam, and again, Archimedean kind of thing, and cut a rectangle so that with the width 1. So if you look at the height x, the volume of the styrofoam here is also equal to x, right? So that's a monomial. So I'm building monomials out of styrofoam. Then I take a piece of styrofoam and cut it in the shape like this. So if this is height h, then this is 2h squared, which means that the area, if I have the height x, again, then this volume is going to be x squared, right? Because this thing is 2x. And so on. So I can build something like this. So this is height x, so this is 3x squared, and that will make this volume x cubed. Okay, so you don't have to go into details, but the point is that if you have I want this shape to be such that in height x, you get the total volume x to power 1, to power 2, to power 3, and so on. Okay, so I build such monomials, which means I build these shapes out of styrofoam, and then I take a rod, rigid rod. Oh yeah, but first I need a polynomial. Let's take a polynomial. A, B, C, D are positive numbers. So just as an example, ax cubed minus bx squared plus cx, I just take this, right? Minus d equals 0. I want to find a root of this polynomial experimentally. I could take a longer polynomial, but Okay, so what I do is I take a rigid rod, mark 0 location on it, and then I put A is the coordinate, and I glue this monomial. I glue this monomial to it. So I glue this styrofoam, I'm sorry, to it. Okay, and then I keep going. So B comes here with a minus sign. But B itself is a positive number. So I put B here, the distance B, right? So B is a positive number. And it comes with x squared. B does, and so I put this shape, glue this shape to here. Well, you get the idea, and then C comes with x, here's the shape x, so I put a coordinate C here, because C comes with a plus sign, so I put it on the right, and I glue this piece of styrofoam to it. And there is D, and D comes with a minus, but I didn't discuss x to the power 0. So that's one little thing. So I put, let me just erase this thing here. I put a little weight 1 at the distance D, okay? I put and now I grab this thing with my hand. So this is my attempt to draw the hand, okay? And I dip this in water. So here's water. And as I dip it, I feel torque from this rod. And I dip it to such a depth that I feel 0 torque. So it doesn't want to tilt. I call this depth X. So X is the depth at which the torque on my hand will be 0. And I claim that that is a root of the polynomial. Why is that so? Because this expression is simply the torque. You see, AX, so you see, so this volume is x cubed. So again, Archimedes says that the force of buoyancy is going to be equal to x cubed. And the arm of this force is A, so ax cubed indeed is the torque. And it's counterclockwise, so I count counterclockwise as a plus. And so on, right? And B, the same thing here. B has buoyancy x squared. The arm is B, but it's on the left, so the torque is clockwise. So therefore, it is counted indeed with a minus as it should. So my claim is basically proven. D, you see, D is the weight. Sorry, D. This weight is down, so it's clockwise. So indeed, as this is minus D is indeed the torque. So I show that this expression is the torque, and when the torque is 0, I have a root. Okay.
Yeah, right. Yeah, I think that's pretty cool. And I think it seems really counterintuitive that there's going to be a large number of roads, right? A large number of equations.
I don't know how to deal with, to be honest, I was kind of lazy and didn't think of how to deal. I mean, I was kind of happy with just the superficial observation, but it would be interesting to see how could one deal with complex roots, for example. That would
yeah, definitely.
I mean, even the simplest thing, x squared plus 1, how can one extend this to use complex? I don't know.
So if you have a polynomial with multiple real roots, say, or with repeated roots, does that sort of manifest itself in the sort of dipping process in any way?
Oh, great question. I haven't thought about it. Like I said, I was very superficial, but I think, yes, I think if you have a double root, you see here the torque is varies linearly, I mean approximately linear with depth. But if you have a double root, I guess the derivative will be 0 also. So that means that the torque will change very, very little, so to speak. So how do I say this? Yeah, I mean, the torque will become very insensitive to the depth. In other words, the derivative of the torque with respect to the height will be 0. So intuitively, it will be felt, yeah. Maybe the torque generically, like it would be, I guess it would not change sign. You see, if you have a simple root, first as you dip, your fist is twisted one way. As you are too deep, it's twisted the other way. At the right depth, it's not twisted. But with a double root, it will be twisted one way, then it will not be twisted, and then as you submerge more, it gets twisted again the old way, right? So it momentarily vanishes, but always is in the same direction. Well, that's a great question. Thank you. I haven't thought about it.
Right, here's another question, whether we'll only get positive real roots this way.
Yes, yes. I think one can get probably negative ones as well if one can extends these. I haven't really, to be honest, haven't thought about it, but that would be a good thing to work out. Maybe when you lift it, but these things have to continue, I guess, these monomials. So it'll be not buoyancy, but suction or something like that.
Yeah. Mm-hmm. Thank you. And does anyone else have any other questions? Here's a suggestion that to get negative roots, you could move the odd styrofoam to the other side of the rod. But yeah, I think that does work. You probably can use the symmetry of the polynomial. You could.
Yeah, actually, somebody probably should write it up. I mean, if one comes up with a nice little note how to deal with negative roots, right, or with imaginary or with complex ones.
Yeah. Yeah. Any other questions? If there aren't any, then I hope it's not too rude to ask you to do another one. Which is, the next one is how to open a wine bottle with a book, and I'd quite like to hear
Of course,
that.
no, I would be happy to do this. In
Yeah.
fact, this was an interesting history. I learned about this when I was an undergraduate back last century, and not even at the end, needless to say, of the last century. And I went to undergraduate in Riga. Anyway, so we had a party one time, and a friend of my friend's apartment, and somebody got a bottle of wine, and and there was no cork, no bottle opener, and but my friend's poor parents were teaching Marxism-Leninism. It's a horrible, horrible thing we had to go through, and he had a shelf with volumes of Lenin's collected works. So he did an amazing thing. Here's the wall. He took this book, one of the things that made me suffer in college. Anyway, we had to learn this stuff. And what he did, he took a book, he smacked this bottle of wine. He pushed the book against the wall, and he smacked the bottle against the book, and the cork gradually started inching out. He kept banging the bottle like this against the wall, and the cork gradually inched out and finally far enough so he could pull it out by hand. And I never understood why is this happening. For a while, I thought it's a cumulative jet. You know what a cumulative jet is? If you take a test tube, a very thin tube, and with water, and there is a meniscus of water because the tube is so small, and you drop it from maybe 1 centimeter on the table. And this water from the walls rushes in, meets together, and shoots a drop of water into the ceiling. From 1 centimeter drop, the water, that's how these cumulative charges for piercing tank armor are, you know, that's the principle they work on. And these cumulative charges can have velocity like enough to leave the confines of gravity, of the Earth's gravity. I mean, it's insanely fast. Of course, it doesn't happen because of the atmosphere, but if they shot this thing into the air up without atmosphere, it could leave the Earth. Anyway, so, and that's what I thought is responsible for the cork inching out. But then one time I started thinking about it again, and I realized that that's not what happens. So what happens is this. So when you accelerate the bottle into the wall, by the way, I should mention that the content of this volume of Lenin advocated economic policies that were responsible for the absence of a corkscrew. And so there was kind of, that was the reason why we had to hit the book with a bottle, right? So it's kind of symbolic justice, I thought. Well, not then, but now, more recently. Anyway, so here's what happens. When you accelerate the bottle, the wine rushes, the wine becomes, goes here, right? And the air is here. And you smack the thing into the book, it abruptly, the bottle itself stops abruptly, but doesn't break because the book is elastic somewhat. But still, the wine keeps going, and that opens, so the air is like a spring, it compresses somewhat, but it opens a vacuum here. And then the wine uncompresses and drives the wine, so the air uncompresses and drives the wine into this cork. The vacuum bubble collapses. It's not elastic, right? It's happy to collapse. And the wine hits this cork like a hammer, because wine is incompressible. It hits the cork like a hammer, and that's what causes the cork to come out. And so basically what you're doing, you're hitting the cork from the inside. So that's, and yeah, I kind of estimated roughly to see, I'm pretty sure it's the correct explanation.
Yeah, thank you. Yeah, it's very interesting. Yeah. Right, I guess a last call for any questions. Yes.
Yeah, quick one. Thank you, first of all, for the wonderful talk. Absolutely enjoyable. It's hard to find questions just because they're so cute and fun, and it's hard to ruin them with how do you do this calculation, which would be the obvious question asked. But I've never heard of these cumulative jet things that you mentioned. They sound cool. Could you say a bit more about them?
Yes. By the way, there is a book, a wonderful fluid dynamics book by Batchelor, where it's described well. But basically what it is if you have two jets coming together, let's say confined jets, right? So this is just like two garden hoses shooting water, one like this and the other like this. What happens is there is a stagnation point where the water cannot, some water will splash back. Most of it, of course, will go forward. And so kind of a very crude picture is this. So I'm sorry, my picture is not so good. Let me redraw it.
I think I understand.
It's understandable, right? So some water goes this way, and it turns out that this speed is very, very large. So it's like a shock.
The speed should be something like 1 over cross section, something.
Yes. So these cumulative charges, they take an explosive and they make a concave surface in the explosive. They coat it with some foil or some metal. And when it explodes, it rushes together. And at one point, there is this kind of collision, and most of it shoots this way with tremendous speed. Yeah, it was a terrible thing. I guess I think it was invented during World War II by the Germans.
By the Soviets, right?
I'm not sure, by the Soviets or by the Germans. Yeah.
Anyway, thank you very much. I was curious.
Yeah. There is also a nice book by Lusternik on fluid dynamics. Lusternik and Shabbat, I think. It's a small, very nice book. It talks about interesting things, like one thing I can say very quickly. For example, if you have a tube, this is what fascinated me in that book, and you imagine a worm that's in this tube snugly fitting, so there is no space, and the tube is perfectly slippery, so is the worm. Can the worm still navigate in this tube? And it turns out that yes, and just imagine the spiral tube, right? So I draw it, and the worm is here, and imagine the worm kind of is like a spring that wants to be straight. Then potential energy of this worm is basically the integral of the square of the curvature over the arc length, you know. So that's the potential energy. And it's clear that if the worm slides this way, its potential energy will increase because it takes, and therefore there must be force that ejects the worm from here, right? So that's a nice kind of problem.
So yeah, thank you very much. Very
Sure.
cute stuff.
Yeah, thanks. Are there any other questions?
I think I didn't catch it. So for the test tube, which two jets collide?
It's not two. It's the water is elevated near the edges of the test tube, and when the tube hits the table, this water goes down and has nowhere to go. So this whole kind of surface meets at the center, so to speak.
That's very helpful. Thank you.
Yeah, sure. And I guess this is what happens probably when you drop, sometimes you drop something in the water and suddenly a drop shoots unexpectedly higher. You can drop, say, a little ball in the water and something will shoot up, water will shoot up higher than you drop the ball from. It's probably the same thing when the falling ball opens a gap in the water and then the water rushes back in, and it's like the same effect, I guess.
Thank you.
Okay, anyone else? Yeah, well, if not, then I think, yeah, I should all say thanks a lot. It was a really interesting talk, a lot of really cool things. Yeah, I think.
Thank you very much for inviting me. It's a pleasure.
Yeah, thanks. Yeah, and thank you to everyone for coming.